Again, the example problem also tells you how to interpolate between table values. And then down here at the airspeed learning objective, find calibrated airspeed. So the first thing we have to do is find calibrated airspeed. We have to use the have to know the position error, and to find the position error we are actually given in the example here the chart. It says here typical position error correction, and that's the one we are supposed to use because it tells us to use this one. And I just want to highlight real quick how to find how to apply that chart. And yeah, alright, I put that chart here on the top left corner. So you enter the chart. Are we still on red here with my colors? Yep, we are. Alright, you enter the chart on the bottom with your indicated airspeed in knots. So let's take an example here. If your indicated airspeed was 325 knots, for example, then you would enter it right here. 350 would be here, so half of it is 325, which is 1/4 between 300 and 340. And then from there you would go straight up till you hit the curve there, where you're looking for that intercept point in that curve, and then from that intercept point you go straight across along one of those lines. That's why they put that little millimeter paper background on there, so that you can basically follow those. That wasn't straight, 100% straight, but you get the idea here. You follow those lines, and then you can read on the left side, on the left side here, you can read your actual conversion as a change in knots, delta VI in knots. That's basically what it tells you here. Airspeed position error correction in delta VI knots. Couple of things to watch out for. First thing, make sure that you know what type of scale is where on that chart. Like for example in this case, the 10 millimeters from here to here on that chart are only 5 knots in change. In this case -5. It's only 5 knots in change, which basically means each little square, millimeter square, is 0.5. okay, so there are 10 little squares in between here, so each of the squares is 0.5, which basically means this is 1 knot here, and then the next 2 squares is the second knot, and then the next 2 squares is the third knot, and so on until you get to 5 knots. So each full knot has 2 squares in there. So when you read the chart, make sure that you count those squares properly and relate them to the scale on that side. Second thing, I already mentioned it a little bit, watch what type of minus or plus symbol is on there, so that you don't apply the correction the wrong way. And the same for the interval in between numbers on the bottom here as well, because this interval is not the same as on the left side. So here are 20 little squares in between 100 and 200, which basically means 10 little squares are 50 knots, which basically means each square is 5 knots for your application of numbers there when reading the chart. So make sure that you properly count the squares. That's why they put them there on those technical charts, so that you can find straight lines for one and count the number of spaces properly, equally spaced, without having to use any ruler or anything, so you can directly read it from the chart without needing additional tools. Once you get practice with those charts, they're actually fairly easy to read and fairly quick representations of what you want to see. Once you get your delta VI as in the example here, where's my click pointer here, as in the example, apply it to your speed, to your indicated speed to get calibrated speed, and again pay close attention to minus or pluses on that speed correction. Then to find equivalent airspeed, you have to start with that calibrated airspeed. So you have to start with what you just found, not with the indicated, but with the calibrated, and you have to apply compressibility correction, which is figure 2.6 in the book. And the correction is the same for all aircraft. So how to read that chart here? Let me move that up a little. Oops, I'm wrong. Let me move that one up a little. Here we go. Okay, and then let's move the other one out of the way completely. Alright, same thing here. That's your 2.6 figure from the book. And you enter the figure in this similar way on the bottom with your calibrated airspeed that you just found in the other example there, or in the other problem. Let's say we had, like, what did we say, 325, and we came up with a free correction, so it's 322 or something like that. Again, 325 would be here, 322 is not quite 5 knots, so it's pretty close to that line here. On the chart, again, pay close attention to how many squares are in between numbers. Then you go up to your altitude that you found earlier. In our example, we were at 2,000 feet, which would be down here. If we go straight up, because this is the 5,000 feet line, so it has to be below the 5,000 feet line. And we already see, like, at 2,000 feet, there's not a whole lot of correction here. It would be like 1 knot or something like that. And again, pay close attention. All those numbers are negative here too. Let's take, for the heck of it, an example of like 25,000 feet. So with that 322 going to 25,000 feet, so that you can see the mechanics one more time. Go straight up along whatever line you used on the bottom till you intercept the altitude line you're looking for, and then from that point go straight over, following along the lines that are printed there, to find your compressibility correction here, again on the left side. And again, it is delta VC in knots, and pay close attention to minuses. Actually, all of those are minus in front. Again, close attention to the number of squares. Again, it's 20 squares for 10 knots, which basically means that 6 squares, like in this case, are 3 knots correction for this one as well. Above the 10, so it's 30 knot correction here, minus 30 knot to be precise, because we want to keep that minus, which basically means if we entered with the 22 calibrated, that's what I said, right? 322 calibrated minus 13, our result would be 309 knots equivalent airspeed. Again, keep track of your units, always indicate what we're talking about. So if the one on top here was 323 calibrated airspeed, we're now talking about, and it's knots, so we can even be more precise here. That's really the big thing. Keep track of your units, keep track which altitude, which speed you are talking about. A number, it doesn't tell us anything unless you attach a unit to it, in all of the examples here. But that should show you real quick how to use those charts. So again, enter at the bottom, make sure that you pay attention to the interval between numbers, how many squares you have to count for. Go straight up till you find the line that you want to intercept, then go straight over and read the correction value on the left side in both of those charts, and make sure that you apply proper minuses and pluses as applicable, and make sure that you again pay close attention to those little squares and how many of those to count for. Alright, and then finally from there to true airspeed, I think, is the next part here. Yep, here we go. Finding true airspeed, again following the example in your example sheet here. You can either do this, use the sigma conversion, or you could use the chart again in the book, which would be down here on the right side. All that chart is basically doing for you is having your sigmas, as it says here, density altitude values already correct calculated for you and put as lines into a chart so that you can enter it and use it the same way you used other charts before. But there's nothing wrong with using the formula. Either way is fine as long as you come up with the right results. So again, using the formula, equivalent airspeed divided by the square root of sigma, and that gives you true airspeed if all your other speeds before were correct. Again, make sure to indicate always what units you are using, what altitudes you are talking about, those kind of stuff, and pay close attention to which direction i.e. which plus or minus the correction is basically working. And then I don't know what a Mach number is required here too. No. The last thing here is dynamic pressure.